Hello everyone, welcome to the video lecture of this course Finite Element Method. This is the second lecture of this first module for this course. So today we will be discussing the different numerical methods, then the concept of the element nodes or nodal points regarding this finite element analysis, then what is the degree of freedom. So all these things will be discussed today in details. In the earlier lecture, we have discussed the basic concept of this finite element method. There we have seen the syllabus of this course in our college, and we have seen that we are having actually total 36 lecture for this course, and we are having total 6 different modules for this 36 lecture. So there actually we have discussed the concept of this finite element method, and we have seen that it is actually a numerical method by using which we find some approximate solution for the partial differential equations. Okay, so regarding this finite element method, we have seen the different steps and the different process or different phases like the pre-processing, solution, and the post-processing. All these things we have discussed in brief in the earlier lecture, and we have seen and we have discussed the historical background for this finite element analysis. Okay, so these things we have discussed in the earlier class and earlier lecture, and in this lecture we will discuss in details the different numerical methods, then the concept of the element and node and degrees of freedom, what is the structural and non-structural part regarding this finite element analysis. So all these things will be discussed in details in this lecture. Okay, so let us start this lecture. So as per our concept of the finite element analysis or finite element method, we know that it is actually a numerical method to find approximate solution of the partial differential equation. So it was actually originated from the need to solve some complex elasticity and structural analysis problem in mechanical, civil, or aerospace engineering branches. Okay, so now in actually structural simulation, this finite element method, it helps to produce stiffness and strength visualization. So this visualization we will discuss while discussing the software simulation part. It also actually helps to minimize the material weight and its cost of the structures. Now, this finite element method, it actually allows for detailed visualization and indicates the distribution of stress and strain inside the body of a structure. So several modern finite element method packages are there, like ANSYS, which we will discuss in our curriculum. So this type of packages, they include specific components such as fluid, thermal, electromagnetic, and structural working environments. So this finite element method, it allows us to construct the entire design in this software. There we can refine as per our requirement this design, and we can optimize that design before it is manufactured. So this is actually a very powerful tool, such type of software simulation. So it has actually significantly improved both the standard of engineering design and the methodology of the design process in different industrial applications. And the use of this type of software analysis or software simulation tool, it has been significant. They significantly decrease the time to take the products from the concept of the designer to the production line. So while designing such type of engineering product and to analyze those, we must take the advantage of such simulation software, where the precision level and the level of accuracy is also very much acceptable. Now here you can see that it is written as numerical method, and 5 different numerical methods are written here. Actually, in any engineering analysis, there are certain requirements like the displacement at certain points, like the stress distribution, the natural frequencies, vibration of regarding the structure. We need to calculate all these parameters for several parts to design and analyze. So different structural parameters or like different non-structural parameters like pressure, velocity, temperature distribution, this type of things, or the fatigue life. So all this type of different parameters we need to calculate while designing and assembling different parts of a product. So these are different requirements that we need to calculate. Now how to calculate? By use of which method we need to calculate all these things regarding different parts of a product. So there are actually different methods for engineering analysis. Those are the experimental method, then analytical method, and the numerical method or approximate method. So what are these 3 different methods? What is the difference in between them? So first we are having the experimental method. In this method we actually use the different prototypes. Now if we want to change the dimension of the prototype, then in that case what we need to do, we have to actually disassemble the entire prototype, and again we need to reassemble it after changing the dimension, and then again the experimental analysis or the testing is needed to be carried out. So that means what? It needs more manpower and more materials. Again this disassemble and again reassembling, again carrying out this experimental analysis, it is very much time consuming, and this process is costly also. So this is the concept of the experimental analysis or experimental method. Next method for engineering analysis, we are having the analytical or theoretical analysis. So in this method actually the various problems, these are expressed by mathematical differential equation and mathematical modeling. So this type of analytical method, it gives us quick and closed form of solution, but it is only used for simple geometries and idealized support and loading condition. Okay, so using of this mathematical differential equation or the mathematical modeling, which are actually very quick to analyze, so these are actually used for some simple geometries and idealized support and loading condition. But what will happen if the shape of the structure is complex? In that case we will go for this numerical method. So what is this numerical method actually? It is an analytical solution can be obtained for certain simplified situation that we have seen earlier in case of the analytical method, but while we discuss regarding the complex situation or the complex body or structure, in that case different material properties of that structure or the boundary conditions are also there. So while analyzing such complex shape along with their material properties or boundary condition, in that case the engineer prefers the numerical method. So this numerical method actually gives the approximate solution, but the result of the solution is within the acceptable limit. So this is the difference in between the experimental, analytical and numerical methods. Now in case of the structural analysis, the formulation for the structural analysis, it is generally based on the three fundamental relations. What are those three fundamental relations? They are equilibrium, constitutive and compatibility. So based on these three fundamental relations, the formulation of structural analysis is being done. So there are actually two major approaches for this analysis. One is the analytical and another is the numerical. So as discussed just now, this analytical approach, it actually leads to the closed form solution which is effective for the simple geometry. It is not applicable or not preferred for the complex shape or complex structure. So in case this analytical approach, it is effective in case of the simple geometry and the boundary condition, loading and the material properties, so which are some not very complex. But what happens in case of the complex shape? Because in reality some simple cases may not be there always. So whenever there is some complex shape, then various numerical methods are evolved for solving such problems which are actually complex in nature. So for numerical approach or numerical method, the solutions that we get, these are approximate, but these are within acceptable limit. And this numerical method that depends heavily on the processing power of the computers actually, and is more applicable to structures of arbitrary size and complexity. So the specification of the computer, these are also very much important while solving such complex shape or the complex geometry with the different softwares. Now it is actually a common practice to use the approximate solution of differential equation as the basis for structural analysis. So this is the main concept of this finite element method actually. Now there are actually different numerical methods which are finite difference, finite volume, finite element, then boundary element and meshless method. These are 5 different numerical methods. Now what is the difference in between them? What is the concept of this finite difference or finite element method? There is a functional approximation. It is actually used for the classical method such as the Rayleigh-Ritz method, which is actually a variational approach, and the Galerkin method, which is a weighted residual method. These are actually based on the functional approximation, but they vary in their procedure for evaluating the unknown parameters. Now this Rayleigh-Ritz method, this is useful for solving complex structural problems, and these are actually encountered in finite element analysis. And this weighted residual method, it is useful for solving the non-structural problems. So in our next lecture we will discuss this weighted residual method or the Galerkin method in details, and we will solve some numericals based on this weighted residual method. What happens in case of this finite difference method? In short, it is known as FDM. This finite difference method, it is actually useful for solving the heat transfer, fluid mechanics and structural mechanics problems. It is actually a very general method and it is applicable to any phenomena for which differential equation along with the boundary conditions are available. So it actually works well for two-dimensional regions with boundaries parallel to the coordinate axis. So in case of this finite difference method, the starting point is that the differential equation must be known before solving. This is the concept of this finite difference method. Now, after that, the region is subdivided into convenient number of divisions. Okay, so this is the concept. That means while starting this finite difference method, the differential equation must be known to the engineer or the designer before the solving. And after that, the region of the shape, that is the computational domain, it is subdivided into a convenient number of divisions. Now the differential equation, it is applied successfully at the various points of the subdivided region. And a set of simultaneous equations, these are generated, which after the solution they lead to the approximate solution of the problem. So this is in brief the concept of the finite difference method. But what is the disadvantage of this finite difference method? It is very difficult to use when the shape or the computational domain or the region they are having carved or irregular boundaries, and it is difficult to write general computer programs based on this finite difference method. Now let us discuss the finite element method. So it has been discussed earlier that this finite element method, it is actually a numerical method or numerical technique to find the approximate solution of partial differential equation. So using this numerical method, we solved several problems of engineering and mathematical physics actually. So in this finite element method or finite element analysis, a body or a structure of having complex shape in which the analysis we will carry out, it is actually subdivided into some smaller elements of finite dimensions called the finite elements. Okay, so this can be seen in this diagram also, that this complex shape, it is subdivided into smaller elements of finite dimensions, which is known as the finite elements. So this it is shown here as a typical element, one almost rectangular shape structure. It is shown as the typical element, which is a subdivided part of the total complex shape. Now this body, this total body or the total structure, it is actually considered as an assemblage of these elements. Now, and these elements, these are actually connected at a finite number of joints, and these joints are called the nodes or nodal points. Here you can see a point at the corner of this typical element, it is denoted as the nodal point. So by the use of this nodal point or nodes, these elements, these are connected together. Now the properties of each type of finite element is obtained, and they are assembled together and solved as a whole to get the solution of the total body or the total complex shape. So you can say that this finite element method, in this finite element method, that instead of solving the problem for the entire body in one go or in one operation, we actually formulate the equations for each finite element, and after that we combine them to obtain the solution of the whole body. So this is the concept of this finite element method. So here what we do, that we do not go to solve the problem for the entire body in one operation. We just actually subdivide or actually break down the total structure in several parts, and after that subdividing this total complex shape into smaller elements, we formulate the equations for each and every finite element, and then we combine them to obtain the solution of the whole body. So this finite element method, it is actually used to solve some physical problems involving some complicated geometries that we get in our real life, and the loading and the material properties which actually cannot be solved by analytical method, because this analytical method, these are actually useful for some simple geometries. And this finite element method, it is extensively used in the field of structural mechanics, of fluid mechanics, heat transfer, mass transfer, electric and magnetic field problems, for such several cases. Now, based on the application of this finite element method, the problems regarding this finite element method, these are actually classified as structural and non-structural problems. So in case of the structural problems, the displacement at each nodal point, it is obtained, and by using these displacement solutions, stress and strain in each element, it can be calculated. So this is the concept of the structural problems. And what happens in case of the non-structural problems? So in case of the non-structural analysis, the temperature or fluid pressure at each nodal point, it is obtained, and by using these values or properties such as heat flow, fluid flow, for each element can be calculated. So this is the basic difference in between the structural and non-structural problems. So till now we have discussed the different methods, that is finite difference and finite element, or the difference in between them, what is the concept, what is the concept of the element or the node or nodal point. All these things have been discussed till now. Now, in this finite element discretization of a domain, it is given in this diagram or figure number 1. So here we can see that the total structure or the complicated structure, it has been divided into some smaller part or some smaller element. Now any continuum or the domain, it actually can be divided into a number of pieces actually with very small dimension, that we have done here in this diagram. We have subdivided this complex shape into some several smaller elements or smaller pieces. So these small pieces of finite dimension, these are actually called the finite elements, which you can see here. It is denoted by the typical element. A field quantity in each element, it is allowed to have a sample spatial variation which can be described by polynomial terms, that we will discuss and we will see in the next slide while discussing the numerical regarding the weighted residual method. That means the original domain, it is actually considered as an assemblage of a number of such small elements, and these elements are actually connected through number of joints which are called the nodes or nodal point. So this nodal point, it is actually denoted here by this arrow sign. It is a joint of this typical element, finite element. Now, while discretizing the structural system, discretizing means to break down or to divide the total structure into smaller part or smaller pieces. While discretizing the structural system, it is actually assumed that the elements, these are attached to the adjacent elements only at the nodal points. So this is the characteristics of the discretization, that all the elements should be interconnected to each other with the help of these nodes or nodal point. Now, each of these elements contain the material and geometrical properties of the total structure. The material properties inside an element, these are assumed to be constant. And such elements, they may be one-dimensional elements, two-dimensional or three-dimensional elements actually. The physical object can be modeled by choosing appropriate elements such as the frame element or shell or solid element or plate element, etc. So after this modeling, all the elements can be assembled to obtain the solution of the entire domain or structure under certain loading conditions. And these nodes are actually assigned at a certain density throughout the continuum of the domain, depending on the anticipated stress levels of a particular domain. And the regions which will receive large amount of stress variation, they will usually have a higher node density than those experience little or no stress. So the discretization or the node density, these are also very much important to accurately grasp the sudden change in the different parameter. So here you can see some degrees of freedom of various elements are shown for 2D truss, 2D beam, 3D truss, all these things are shown here. Now what is this degrees of freedom? A structure can have infinite number of displacement. It is known to us, we have studied this part in strength of materials, or actually in engineering mechanics we have studied this concept of the degrees of freedom, that a structure can have infinite number of displacement and approximation with a reasonable level of accuracy. It can be achieved by assuming a limited number of displacement. Now this finite number of displacement is the number of degrees of freedom of the structure. This is the concept of the degrees of freedom actually, that for any considered structure it can have any infinite number of displacement, but the approximation with a reasonable level of accuracy, it can be achieved by assuming a limited number of displacement. And this finite number of displacement, it is actually the number of degrees of freedom for the structure. Suppose if we consider an example that the truss member will undergo only axial deformation, which you can see here in the first diagram that is written as 2D truss. The truss member will undergo only axial deformation. So that means what? The degrees of freedom of a truss member with respect to its own coordinate system will be only one at each node. Now if a two-dimensional structure is modeled by truss element, then what will happen? Then the deformation with respect to structural coordinate system will be 2, because it is in case of two-dimensional structure, and depending on the finite number of displacement, we can assume the number of degrees of freedom for that two-dimensional truss member. Okay, so in this way the degrees of freedom for various types of elements which are shown here, like 2D truss, beam, then 2D grid, 3D frame, then plate, shell, membrane, different types of degrees of freedom for various elements are shown here. So here you can see U, V, W, these are written, and theta x, theta y, theta z, these are also written here. So what does they represent? They actually represent this U, V, W, they represent the displacement, and theta x, theta y, and theta z, they represent the rotation of these different structures or different elements here. So there are actually different types of engineering analysis. So First, we can say that the structural analysis of a section. So the structural analysis, it consists of some linear and non-linear models. These linear models, these are some simple parameters, and they assume that the material is not plastically deformed. In case of the structural analysis, we assume that the material is not plastically deformed. Non-linear models consists of stressing the material past its elastic capabilities, and the stresses in the material then vary with the amount of deformation. So this is the concept of the structural analysis part in case of the engineering analysis. So this is actually a screenshot of the structural analysis of a section with the help of the software simulation. So this type of thing we will also perform while discussing the software simulation part in the 6th module of this course. Next we are having some vibration analysis. It is actually used to test a material against random vibrations, shock and impact. So each of these incidences, this may act on the natural vibrational frequency of the material, and it in turn may cause the resonance and subsequent failure. The analysis of vibration in bridges, it is shown here with the help of a diagram of the software simulation. Next, the fatigue analysis also can be done, and this fatigue analysis, it helps the designers to predict the life of a material or structure by showing the effects of cyclic loading on the specimen. In such type of fatigue analysis, it can show the areas where the crack propagation is most likely to occur, and the failure due to the fatigue may also show the damage tolerance of the material. So optimization and some precautions can be done or can be achieved using the software simulation. Then we can do the heat transfer analysis also. Some heat transfer analysis models the conductivity and thermal fluid dynamics of the material or the structure, and this may consist of a steady state or transient transfer. And the steady state transfer refers to constant thermal properties in the material that yield linear heat diffusion. So here you can see in case of a shell and tube heat exchanger, the thermal analysis using the software simulation has been carried out. The movement of the hot and cold fluid, these are actually can be visualized while the simulation can be performed using this software analysis. Now, how this finite element method helps the design engineer? So there are several advantages or important advantages to the design engineer that FEM offers. That it is easily applied to complex irregular shape objects composed of several different materials and having complex boundary conditions. These are applicable to steady state, time dependent and eigenvalue problems. This eigenvalue and eigenvector, these are known to us. We have studied this in engineering mathematics. These are applicable to linear and non-linear problems. This finite element method. And one method regarding this finite element, it can solve a wide variety of problems, including the problems in solid mechanics, fluid mechanics, chemical reactions, biomechanics, heat transfers, etc. So these are some important advantages of finite element method. Now, how this finite element method helped the design organization? The simulation using this finite element method also offers important business advantages to the design organization, like reduced testing and redesign costs, thereby shortening the product development time. Next, identify the issues in design before the tooling is committed, and refine components before dependencies to other components prohibit changes. We can optimize the performance before prototyping. and discover the design problems before litigation. So these are the different advantages which can be achieved by finite element method. So today in this lecture we have discussed the different numerical methods, the concept of this finite difference, finite element method in details. After that we have discussed the concept of the element and node, how these elements are connected by the help of node, what is the discretization, then the different degrees of freedom for different structure like strass, membrane, then frame, all these things have been discussed. Okay, so this is the end for this lecture, and in the next lecture we will discuss the weighted residual method, and we will solve two different numericals based on the concept of this weighted residual method. So this is the end for this lecture here.